Hello, good morning, good afternoon, good evening, everyone. Welcome to a new lecture on machine learning. I'm so appreciative to your time for watching this video lecture. In the previous lecture, we learned about different categories of machine learning: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So the first category was supervised learning, and in this category, we had two main tasks: classification and regression. Today, we will be diving into one of the fundamental algorithms in predictive modeling world, that is linear regression. This concept formed the bedrock for understanding more complex supervised learning models, and we will explore its theory, application, and optimization. Here is the roadmap for the today's lecture. We will start with formal definition of regression and linear regression. We will look at its use cases across different industries, and we will discuss the criteria for selecting this model. Then we will spend a significant amount of time on mathematical representation. We will learn how the model works under the hood. Finally, we will cover the key concepts like errors, evaluation metrics, and gradient descent as optimization algorithm. As its core, regression analysis is a form of predictive modeling. So the goal is to investigate and model the relationship between one dependent variable that is considered as target and also independent variable or variables, one or more independent variables, that is the predictor. So you can see here a variety of regression type that we listed here, but our focus is on linear regression. We will mainly look at simple linear regression. Linear regression is a model in the category of supervised learning, as I said already. In supervised learning, we have mainly two tasks, that is classification and regression. Classification is used when the output is discrete. For example, in spam detection, it's not an spam, it's an spam, right? However, in case of regression, we use this one when the output is continuous. For example, price estimation, time, height, weight, etc. We need to have a data set to train this model. So linear regression specifically quantifies the linear relationship between the predictors and also the outcome variable. You will often hear it referred by the name of ordinary least square or multivariate regression or multiple regression. The main application areas include forecasting future values, for example, sales or stock price prediction, and also determining the strength of predictor. This is input factor that have the biggest impact on our target variable. There are mainly two types of linear regression. One is simple linear regression and another one is multiple linear regression. In simple linear regression, we have input x. This is a single variable. However, in multiple linear regression, we have multiple inputs. The key application of linear regression, for example, we want to determine the strength of predictor. We want to see which factor have the biggest influence on the outcome. Or we want to forecast and we want to go for trend analysis. We want to predict future value, or we are interested in understanding general market direction, for example. So linear regression is highly versatile across many domains. For example, in business, finance, we can go for sales and profitability. We want to evaluate sales performance. We want to estimate future progress. We want to generate insight on consumer behavior. We're gonna assess risk factors in financial service and insurance, like critical application it is. We can go for determine the effectiveness of pricing, promotions, and marketing campaigns on sales. For example, a classical and intuitive example is predicting house price based on, for example, their size. Before implementing, we must ensure linear regression is the right tool, whether we selected the linear regression as our correct tool for our dataset based on dataset and objective that we have. So our target variable must be continuous. As I said, for this clip, we must go for classification. For example, we want to go for price or temperature, not a category. If it's a category, we should go for classification. This linear regression may be weaker in minimizing error compared to more advanced nonlinear models. This linear regression is highly sensitive to outliers. Outliers is a data that is not following the distribution of our data. For example, if we have a data set of house price, and if, for example, 2 or 3 or 5 of houses, they are out of range. For example, the range is from 100,000 to 1 million, and suddenly 5 of them are $1 billion, right? So these are called as outlier. And this linear regression is highly sensitive to outliers, and these can drastically skew the line and disrupt the results. What are the strengths of this linear regression? So on the positive side, this linear regression is not computationally expensive. So we can easily train, and this linear regression remarkably transparent and it's easy to interpret because it has a simple mathematical calculation and formulation. So this linear regression is a great starting point for any analysis. Linear regression is a linear model, as its name suggests. In other words, we are interested in training a model that assumes a linear relationship between what? Input and output. Input is x, output is h theta x, or you can say y or anything, right? So in this equation that you can say this is linear, we don't have a square or cube here. So the maximum power is 1. So h theta x, theta 0 plus theta 1 x. If we want to draw a line, we need to know two things, slope and intercept. So in this model that you can see here, h theta x is the output that we determine based on x. H theta x is our model's prediction, for example, price of a house. Then we have theta 1 x. Theta 1 is the slope of coefficient. This is, you can say, the weight. This weight determines the impact of input x on the output. Then we have theta 0. This is the constant term. Also, we call it as y-intercept, right? It's a kind of constant, or you can call it as y-intercept. This theta 0 is the predicted value when x is equal to 0. Let's consider one example of bicycle riding. We are interested in the prediction of travel distance from a specific point. We can show this one as h theta x, theta 0 plus theta 1 x. Or you can say the distance traveled is equal to theta 0. Theta 0 is the coefficient, and theta 1 is the slope of the speed. So if we consider time as constant, for example, in 1 hour time, totally is, for example, 60 minutes. Then if the speed is 10 meters per second, this gentleman can travel 36 kilometers. Now, if we increase the speed to 20 meters per second, then he can go 72 kilometers. Then, based on this data that we have and based on the model of this guy that we have generated, we want to see if the speed is 30 meters per second, what is the travel distance? We want to predict distance travel given a constant time interval. If we double the speed, we double the distance covered in that time. This shows a positive relationship, right? So as the speed increases, the travel distance increases as well. Positive relationship. Therefore, the coefficient theta 1 will be positive. It results in a positive slope. So the line moves upward from left to right. This is our regression line. So now let's change, and this time we consider distance as constant, right? It means we want to see, for example, 100 meters or anything, right? It can go in 100 seconds. If the speed is 20 meters per second, it can go in 50 seconds. Next, we want to predict if the speed is 30 meters per second, in how long time it can travel, it can ride this 100 meters. This time, the relationship is negative because as speed increases, time decreases. So this is negative slope. So we show this like this one. This is negative relationship. It means if the distance is constant, we are predicting the time taken, that h theta based on speed. So if we increase your speed, the time it takes to travel the fixed distance decreases. And we consider this one as negative relationship. So the resulting line has a negative slope. As you can see, the slope is negative. Let's see how it works using a simple numerical example. Here is our data set. We have x and we have h theta x. So if it is 1, then it will be 3. So you can see here 1 and 3. This is one data point. Then 2 and 4. Then 3 and 2. Then 4 and 4. And 5 and 5. This is a data set, right? We showed it in a scatter plot. It means if our x is equal to, so this is x and this is h theta x, right? If it is 1, then the output is 3. If it is 2, this is kind of data set that we have, a simple data set. We would like to have a representative line of our data as a model that has minimum distance to the data points, right? How we can draw a line for this data set to represent this data set that it has the minimum distance to each data point, right? So this is called as error, right? Or distance between each data and the line, okay? So we want to have a line. How to draw a line? We can draw different lines here, right? So two important things is where to start the line and what should be the slope. Okay, this is our objective. We want to find two things, right? Intercept as theta 0 and slope as theta 1, okay? So the first step in linear regression often involves calculating the mean of both variables. So the mean of is x is 3. The mean of h theta x is 3.6. So this point is there. So we can draw this line. This is just starting, okay? So a key property of the line of this fit found by the least square method is that it must pass through the mean point. So our mean point is 3 and 3.6. So the line should pass the midpoint, but how to find it will fit well. For example, we can draw a line from this one, right? That is passing mean point, right? This one, this one, this one, right? So the intercept and the slope is important, where it should pass, okay? So there are infinity possible lines. Which one is the best line? The best line means has the lowest distance to each data point. So you can see this animation here. This is data points. So we have several data points here, and we want to have a line. This shows the line. So you can see here, we can adjust this line to have the minimum distance to each data point. We use regression equation to find the best line. So we can say h theta x is equal to theta 0 plus theta 1 x. To find this equation for our data, we need to find our slope and coefficient. So theta 0 and theta 1, they are the values that we should find. But how do we find this coefficient? That is called as learning procedure. Finding the best theta 0 and theta 1 is the learning procedure. To find optimal values for our parameters like theta 0 and theta 1, we have two primary methods: ordinary least square method and gradient descent approach. In the first method here, this is a kind of analytical and also closed form solution. This directly calculates the optimal parameters using a set of formulas. And in the second one, this is a kind of optimization. This is a kind of iterative optimization algorithm, and this method slowly and repeatedly adjusts the parameters in order to minimize the error. So we will cover both of them. Our goal is to find or predict the best fit line using the least square method. First, we need to find equation of best line. That is, we need to find equation for theta 0 and theta 1. So for theta 1, it is x minus x bar. X minus x bar, mean, right? Each data point minus it. And actual value and mean of the data divided by sum of x minus x bar square. So here we see how to calculate. We have this data set. This is our data set that we had x and h theta x. What we do, we will calculate the mean. So it was 3 and 3.6. Yeah, 3 and 3.6. Then here, x minus x bar, right? So 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. Then h theta x minus h theta bar. So 3 minus 3.6, 4 minus 2, 4, and this one. Then this one square, right? 2 square, 1 square, 0 square, this one. So we will sum up them, 10. Then x minus x bar, this one, multiply this one. So minus 2 multiply this one, minus 1 multiply this one, 0, 0, 1, 4, 2, and you sum up them together. So we have all the terms, right? We have already calculated this one as 4. Then x minus x bar square, x minus x bar square, we have 10. So theta 1 is 4 divided by 10. We already found 4 divided by 10 for this one as 0.4. Then we need to calculate the theta 0, okay? So we will put it here. H theta x is equal to 0.4x multiplied theta 0. We already found 3.6 as the mean of this one. So this one should be 0.4. So 0.4, this is the mean of this one, and this is the mean of x, theta 0, 3.6, 1.2, and theta 0, then theta 0 is equal to 2.4. So based on this ordinary least square method, we found that the regression line is h theta 0 is equal to 0.4x plus 2.4. So now we will go for prediction based on this regression line, okay? So 2.4, 0.4x, right? So we will calculate, this is predicted, right? This is actual, this column is actual, and this is predicted using this model, right? It means we will put this x as 1 here. So it means it will be 2.4 plus 0.4. So it will be 2.8, okay? So for this point, the predicted is here. For this one, 2 will be here, right? So the predicted is here, 2 and 3.2. So originally, it was 2 and, but it is 3.2. So this one, originally, it was 3 and 2, but based on this model, if we put 3 here, then we will find it as 3.6. For 4, it is the same, right? So for 4, it was 4, and now it's the same. So the distance is 0. For 5, it was 5, but now we find it as 4.4. And for 6, as a new value, we predicted as 4.8. So these are the predicted values based on this equation that we found. Now, the task is to calculate the distance between actual and predicted value. So you can see these are actual and this is predicted values. The main objective is to reduce the distance. How to reduce the distance? By adjusting the line. We cannot move these data points, right? These data points are fixed, but we can adjust the line. How to adjust? By changing the intercept and slope. Then the line with least error will be the line of regression, or you can say the best fit line. So again, this vertical distances that you can see, these red dashed lines, these are the distance between an actual data point and our line of best fit, that we call this one as error, or also this is called as residual, or you can say error. Our primary objective in all of machine learning is to build a model where the sum of these errors is as small as possible. That is called optimization. So this is the fundamental principle of minimizing the cost function, or you can say loss function. An important assumption of linear regression is homoscedasticity and heteroscedasticity. Homoscedasticity, it means the variance of the error is constant across all levels of input. As you can see here, this is when the spread of the residuals increases or decreases systematically with the predictor, so we call it as heteroscedasticity. This is problematic because it violates the OLS assumption and often results from issues like outlier, misspecified model, or unaddressed skewness in our data. So once again, there are some possible reasons for heteroscedasticity. So it may occur in those data sets which have large range between the largest and the smallest observed value. For example, when we have outliers, or when the model is not correctly specified, or if observations are mixed with different measures of scale, or when incorrect transformation of data is used to perform the regression. So when there is skewness in the distribution of regressor, and also maybe some other sources. What is the meaning of skewness? Skewness in probability theory and statistics, it's a measure of the asymmetry of the probability of a real value random variable about its mean. Now we're going to learn an iterative approach like gradient descent that is in the other side of analytical OLS approach. In an iterative algorithm, the model does not calculate the solution directly. Instead, it starts with a random line, then it calculates the error, and then slowly and repeatedly adjusts the parameters like theta 0 and theta 1 until the minimum total error is achieved. Any model may or may not work well. Once our model is trained, we need metrics to quantify its performance. The most important one for linear regression, you can see here R square, adjusted R square, MSE, RMSE, MAE, MSPE, MAPE, and RMSLE. We can categorize them into absolute error metrics and relative goodness of fit metrics. For the case of absolute error metrics like MSE, RMSE, and MAE, they quantify the average size of the error in the unit of our target variable. On the other side, relative goodness of fit metrics like R square and adjusted R square, they tell us the proportion of the target variable's variance explained by the model. We will see in practice. So the first one is MSE, mean squared error. This is the most common loss function for regression. MSE is the average of the square difference between the actual value and the predicted value. Why we say squared? Because we want to ensure all errors are positive. So more importantly, this MSE heavily penalize large errors, or you can say outliers. So the model prioritizes reducing the outliers. The result is a single number that summarizes the model's error. So MSE 1 by n, h theta x, this one. So this is the actual, and this is the predicted, right? And n is the number of data. Then we go for R square. R square is often called as coefficient of determination. R square tells us the percentage of dependent variables variance that is explained by our model. It is calculated as 1 minus sum of I to m h minus predicted square and divided by I from 1 to n h theta x minus bar, right? We calculate R squared as 1 minus the ratio of unexplained variance. Unexplained variance is the error of our model to the total variance, the error of a model that just predict the mean. So R square range from 0 to 1. For example, if our R square is 0.8, it means 80% of variability is explained by our model. So when it is 0, the model explains none of variability of response data around its mean. When it is 1, the model explains all the variability of the response data around its mean. The higher R square, the better model generally fits the data. It means close to 1 is good. A major drawback of R square is that it always increases when you add a new predicted variable, even if that variable is statistically inefficient. So we go for adjusted R square. The adjusted R square corrects for this inflation by penalizing the inclusion of predictors that do not significantly improve the model's fit. So this R square is a more reliable metric when comparing models with different numbers of predictors. Adjusted R square is 1 minus R square, n minus 1, n minus k minus 1, where n is the total number of observations and k is the total number of predictors. So here we want to go for R square. What we do here, R square based on the equation 1 minus h theta xi minus predicted, h theta xi minus mean. Okay, so we can calculate this one in this way. This is our actual data, h minus mean square predicted, h minus predicted h minus predicted square, right? So we will simply calculate it. So we will go for sum of this one, sum of this one. 3.6 divided by 5.2 is equal to 0.69. Okay, so in here we calculated the unexplained variance, that is the sum of square error from our line based on this equation, h theta x minus theta hat. It means predicted, so it is 3.6. And also we calculated the total variance, that is the sum of square error from the mean, that is 5.2 based on this calculation, right? And by plugging these into the formula, we come up with 0.69. This means our model explains 69% of variability in output. While not perfect, 69, it's a good initial fit, but it suggests that other variables may be needed to explain the remaining 31%. So let's go back to the least square principle. Regardless of whether we use the OLS formula or gradient descent, our fundamental objective is to minimize the total error of the model. We quantify this total error as the sum of square errors, right? Then by squaring the distance, we ensure that both positive and negative errors contribute equally and large errors are strongly penalized. So here we can see d is equal to sum of errors, right? These are the errors. So di is the distance between the line, and so this much is this line. So we go for sum, and m is the total data points. For your reference, OLS, ordinary least mean square, we use it to find the coefficient. So this formula that you can see here, theta 1 and theta 0, we're going to find theta 1 as slope and theta 0 as intercept. These two equations guarantee that calculated theta 0 and theta 1, they are the unique parameter that result in the absolute mean sum of square errors for a given data set. As I already told you, x bar is the mean value and h theta x bar is the mean value for the output. So here, our hypothesis is h theta x is equal to theta 0 plus theta 1 x, and this theta 0 and theta 1, these are the parameters that we want to find. So we want to find out theta 0 and theta 1 in such a way that the distance between data points and the line is minimized, right? So it means which line is the best line, right? So we will calculate the error between data points and line, and we will select the best line, right? The best line which has the minimum distance with the data. The problem of training a linear regression model is an optimization problem. So this is our model. We must search for the space of all possible values for parameters theta 0 and theta 1. So as you can see here, changing these parameters like theta 0 and theta 1 dramatically changes the line position and slope, these leading to a different errors. So our goal is to find the perfect combination that minimizes the error. If we consider, for example, theta 0 as 1.5 and theta 1 as 0, it will be this line. If we change it and we find theta 0 as 0 and theta 1 as 0.5, this will be this line. If we change the theta 0 as 1 and theta 1 as 0.5, this line, right? So if our data is like this, right, then we will calculate the distance, sum of error distance between each data point and line. Which line give us the minimum error will be the best line. So here is our cost function, also known as loss function. The cost function or the loss function is our mathematical definition of error. This is essentially the MSE, mean squared error. The factor of 1 by 2n that you can see here, this is included to simplify the math when we take the derivative later. The absolute and singular goal of our model training is to find a parameter value that minimizes the cost function, right? So what will be the value of theta 0 and theta 1 that j is minimized, the minimum value? What is j? 1 by 2n, sum of predicted minus actual. Predicted minus actual, right? For this one, we turn to gradient descent. So the idea is to choose theta 0 and theta 1 so that each theta x is close to y for our training example of x and y, for example. To do so, we need to solve an optimization problem. So once again, cost function is the function that measures the performance of our model for any given data. Cost function, in fact, quantifies the error between the predicted and actual value, and it presents it in form of a single real number. So now I want to explain gradient descent algorithm. Imagine you are blindfolded on a mountain and you need to find the valley flow, the minimum cost. So you are here, you can't see around, maybe it's fog, right? And you want to come to this point, yeah? It's a safe point here. The only thing you can do is feel the slope beneath your feet. This is the essence of a gradient descent algorithm. So by checking the slope, you can come to this point. So gradient descent is an optimization algorithm, and we use it to iteratively find the parameters that minimize the cost function. The gradient descent algorithm start at an initial weight in each step. For example, you are here, then we calculate the gradient, that is the slope, right? And we take an incremental step in the opposite direction, in this direction, negative. If we go to positive, we will go to this point, right? But we are interested in lowest or global minima. That's why we will come to this point in opposite side, and we will go toward the minimum cost. This algorithm is also known as steepest descent. When we are in this mountain, we take a step in a descending direction and we iterate this process until we reach the lowest point. Gradient descent, as I said, the kind of optimization algorithm, and we use this gradient descent to train a machine learning model. Gradient descent is essentially based on convex function and tweaks its parameters iteratively to minimize a given function to its local minima. In here, we use gradient descent to find the values of a function like parameters or coefficients that minimize the cost function as less as possible. To find the local minima of a function using gradient descent, we must take a step proportional to negative of the gradient. So if we are here and we calculate the gradient, so we should go to opposite side. If we go to this side, it will be gradient ascent. The next time we calculate the derivative, we come to here, next time, and then here we will stop because gradient will be equal to 0. So if we have only one parameter, then theta1 will be equal to theta1. It is updated, not equal updating, right? Theta1 is equal to the previous value of theta1 minus alpha derivative of loss function with respect to theta1. So derivative is the slope of this line that you can see here. The slope of this line is positive, right? So we will go for the negative side. Here you can see the core mathematical update rule for gradient descent. The algorithm repeats until convergence, and the term that you can see here, partial derivative of j theta 0 and theta 1 with respect to theta j, this is the partial derivative, and these compute the slope of the cost function with respect to the parameter theta j. This is our gradient. Then we update the parameter, so this is update. It means previous theta j minus alpha. This is called as learning rate, right? So learning rate or step size multiply the gradient. So this negative, we want to go descent. If it is positive, we go ascent, right? So the goal of gradient descent is to minimize the given cost function, that this is our cost function. So here, the gradient, the partial derivative of cost function with respect to theta j is equal to, we just bring cost function here. This j is our cost function, right? 1 by 2n predicted minus actual, right? Which is equal to derivative of this one with respect to theta j. 1 by 2n theta 0 for this one, theta 0 plus theta 1x that we predicted minus the actual one. So for theta 0, if j is equal to 0, then the derivative of j with respect to theta 0 is 1 by n predicted minus actual. If j is equal to 1, then again derivative of this one, 1 by n, and this time we have xi here because here it was 0, we don't have it. We repeat these two steps until convergence. This is kind of updating at the same time, right? Theta 0 is equal to theta 0 minus the learning rate, and this is the gradient. Theta 1 is equal to theta 1 minus learning rate 1 by n data points, and this is the gradient. In cost function, we may have multiple theta parameters. So this expression of updating with subscript j means to update all of the parameters at the same time, right? It is absolutely critical that theta 0 and theta 1 are updated at the same time. This is done by calculating the new values like temp 0 and temp 1. So temp 0 is equal to theta 0 minus alpha derivative, theta 1 minus alpha derivative. Then theta 0 is equal to temp, and this one is equal to temp 1. It means we are updating at the same time, right? So we have to update them at the same time simultaneously. If on the other side we go for sequentially, then the calculation of theta 1 would use the newly updated theta 0 from the same iteration, and this is incorrect for this algorithm. When we have only one parameter, like theta, we can plot the dependent variable cost on y-axis, as you can see here. For example, predicting age based on the hair color. So this is for one parameter, and this is y or predicted, and this is x, and we go for the gradient descent in this way that we can come to the convergence. So this is simple 2D plot, and this shows the model starting at an initial point with some weight, and then it stepping down to the curve toward the global cost minimum, right? This because this one as global cost minimum. The steps get smaller as the slope flatten near the optimal. So you can see here the steps become smaller and smaller because the gradient is become smaller and smaller. If there are two parameters, we can go for a 3D plot that you can see here, and we can go for this 3D plot with cost on one axis and two parameters like theta along the other axis that you can see here. And this one is a counter. This shows a 3D plot in 2 dimensions with parameters along both axes and also the response as a counter that you can see here. So we start from here, then finally we come to this point. We may start here, then finally we come to this point as the global. Using the gradient descent, we already found the direction using this gradient to come down, right? So we add minus to come down. Now we must decide the size of the step we must take, right? So if we are here, and our step size is very small, right? Like this, finally we can come to here. The problem is time, right? It takes long time. If we take big steps, then it go for overshooting, right? So we should go for moderate learning rate. So large learning rate goes for overshooting. Small, it takes long time. If the learning rate is too high, as you can see here, we might overshoot the minimum and we keep bouncing without reaching the minimum. If the learning rate is too small, the training might turn out to be too long. So we should go for a moderate one. So you can see here, we can see the relation between the learning rate and conversion. If it is very high, it will be like this. If it is low, it takes very long time. It is high, it will be something like this. And if it's a good one, this red one, it shows a good one. So as the gradient descent decreases while moving toward the local minima, the size of the step also decreases. So the learning rate alpha can be constant over the optimization, and we don't need to change it. It will be get smaller and smaller. So the cost function may consist of many minimum points. As you can see here, this is global, this is local, this is local. The gradient descent may settle on any of the minima. Why? Because when the gradient becomes zero, it will stop here. It will not pass, right? This is one drawback of the gradient descent. So this depends on the initial point. If we start at this point, we will stop here. If we start at this point, we will stop here. If we start at here, we will come to the global minima. Remember, our goal is to come to global minima, not local minima. So the optimization may converge to different points with different starting points and learning rate. For a cost function that is convex, like this one, the gradient descent guaranteed to find the global minima is here. However, for more complex models that you can see in this animation, the cost function can be non-convex. It means it has many local minima. One is here, two is here, and third one is here, that is global minimum. In this case, gradient descent only guarantees finding the minimum in immediate vicinity where it starts. The gradient descent in this case does not guarantee the absolute global minima across entire parameter space. This is one problem, and the solution for this one is other grade, adaptive gradient descent, or simulated annealing. Okay, that's all. Thank you very much for your attention. I hope you now have a solid understanding of linear regression, hypothesis, OLS, and gradient descent. Please feel free to share with me any questions, comments, or concerns you may have via this email. Thank you, and see you in the next lecture.